Hi everyone, welcome back to another video regarding your course Chemistry for Engineers. Again, this is your instructor, Engineer Janaika A. Tapiador. So far, we have already learned about the energy that actually covered your module number 1. And now we start covering your module number 2, which is entitled Engineering Materials. So your module number 2 are about the engineering materials that are commonly used in your engineering practices. So these are the topic learning outcomes that you have to achieve after this particular module. So it says here, at the end of module 2, the students shall be able to discuss the different engineering materials, particularly your crystals, metals, polymers, and nanomaterials, and of course solve problems on crystal lattices. The problem solving of your crystal lattices will be covered in the laboratory. So these are the module content. The very first stop is the basic concepts of your crystal structure, followed by your metals, and then your polymers, and then your engineered nanomaterials. So for this one, for this video rather, we will only be covering the basic concepts of your crystal structure. These are the topic contents for this particular video. We start with solids and modern materials as an introduction to the basic concepts. It says here, modern devices like your computers and cell phones are built from solids with very specific physical property. As an example, the integrated circuit that is at the heart of many electronic devices is built from semiconductors like your silicon, metals like copper, and insulators like hafnium oxides. Your hard drives, which store information from your computer and other devices, they actually consist of a very thin layer of magnetic alloys deposited in your glass substrates. Your scientists and your engineers almost turn exclusively to solids for materials used in many other technologies. So it's very obvious that, for example, the current device that you're using to watch this video, they are actually made out of solids. And of course, all of those materials that you're holding right now are possible because of the solids that we could harness from nature and turn them into modern materials that we could use in order to help us in our daily lives. So it says here, alloys for magnets and airplane turbines, semiconductors for solar cells and light-emitting diodes, polymers for your packaging, and biomedical applications. So chemists have contributed to the discovery and development of new materials either by inventing new substances or by developing the means for processing natural materials to form substances that have very specific electrical, magnetic, optical, or mechanical properties. Of course, when we want to use something, diba? For example, we want, for example, your gadgets, your integrated circuits inside your gadgets. There are specific solids that we need to use in order for us to meet the criteria that is needed. So your solids, they have different properties, which we will be covering later on. And whenever your chemists, scientists, and engineers want to use a certain solid, they have to make sure that it actually conforms to the needed criteria, like your electrical property, optical property, magnetic, mechanical, and even sometimes chemical properties. So let's go to the second topic for this particular content. So the classification of your solids. So our solids are very different from each other, diba? As you can see here in the first statement, they can be as hard as a diamond or even as soft as wax. Some readily conduct electricity while others do not. Some can be manipulated into the shapes that you want, while others are very resistant to any change in shape. The physical properties as well as the structures of your solids are dictated by the types of bonds that hold the atoms in place. And we can classify your solids according to those forces. So you have four classification of your solids, mainly your metallic solids, ionic solids, your covalent network solids, and of course your molecular solids. Now let us take a quick look at each one of them. So your metallic solids, when we say metallic solids, they are held together by a delocalized sea of collectively shared valence electrons. This form of bonding allows metals to conduct electricity. It is also responsible for the fact that most metals are relatively strong without being brittle. So your metals are very specific kinds of solid because they actually have like parang, di ba? Of course, you already know that your atoms, or rather your atoms, is composed of your nucleus and your electrons. Now, in metallic solids, the electrons from atom to atom are being shared, meaning they can travel from one nucleus to another. That's why they call it your delocalized sea, parang kasi masyadong madami siya, sea of collectively shared electrons. Now, because your electrons can travel from one nucleus to another, parang free-flowing yung electrons, that's actually the reason why most metals this form of bonding allows metals to conduct electricity. That's why we turn exclusively to metals when we, for your copper wires, for example. Kasi diba, your electrons can flow. And for your gadgets, we're actually using metals because of this particular property, wherein you have a sea of electrons. But we'll talk about metals more in the upcoming video since we have a very specific topic for this. So the next type of solid is known as your ionic solids. When we say ionic solids, from the name itself, it is composed of ions. And these are held together by the mutual attraction between your cations and anions. Differences between ionic and metallic bonding make the electrical and mechanical properties of ionic solids very different from those materials. So when we say ionic solids kasi, parang these are made up of one metal and a non-metal. So the bonds are, kumbaga, you have, when you say ionic kasi, the electron, one element will be sharing, will be giving up rather the electron. Will be giving up the electron to the other element. So for example, you have your NaCl here. Your Na has a charge of +1 and your chlorine has a charge of -1. So ibig sabihin po, si sodium ion dito, i-give up niya yung electron niya papunta kay chlorine para po they could reach your stability. So, it's giving up of electrons, and yung pag-give up ng electrons na yon, yun po yung mag-make ng bond nilang dalawa. And you have the third one, you have your covalent network solids. When we say covalent network solids, they are held together by an extended network of covalent bonds. Now, when we say covalent bonds, ibig sabihin po dito yung electrons, sinishare po ng dalawang element. Diba? Kung sa ionic bond po, yung electron is i-give up. However, dito sa covalent bond, mag-share sila dun sa electron. So it says here, this type of bonding can result in materials that are extremely hard, like diamond, and it is also responsible for the unique properties of your semiconductors. Your covalent network solids, ito po yung mga strong solids. Kasi nga, as sinishare kasi yung electron. So, parang yung force mas malakas compared to your ionic solids. So, that's it. And of course, the last type are your molecular solids. When we say molecular solids, on the other hand, these are held together by your intermolecular solids. When we say intermolecular forces rather. And when we say intermolecular forces, this is the type of force that holds molecules together in a liquid or solid. An example of this is your water. So, dito, water. Diba? Yung water nyo kasi, nag-exist siya with an oxygen and two hydrogen atoms. So, they are being held together by your intermolecular solids. It exists as a molecule. So, let's go to the third topic of this content. You have the structures of solids. It says here, solids have different structures contributing to their different physical and chemical properties. And these structures are classified into two, mainly your crystalline solids and your amorphous solids. Excuse me. Let us take a closer look at each one of them. When we say crystalline solids, these are solids having regular, ordered arrays of components held together by uniform intermolecular forces. Now, the atoms in this type of solid are arranged in an orderly repeating pattern. These solids usually have flat surfaces or faces that make definite angles with one another. So as you can see, you have here examples of your crystalline solids. You have your galena. And if you take a look at the picture, para siyang tumutubo siya in such a way na parang you have little tubes. Diba? Ganyan. And you also have your quartz. Tapos yung quartz naman parang tumutubo siya in a way na parang pa-pyramid yung kanyang structure. And you also have your pyrite. Medyo magulo siya, but there's actually a certain pattern to this. Kaya mong bigyan ng pattern to, your pyrite. So, para siyang much more like the structure of your galena as well. Kumbaga parang may mga nagpo-form na cubic shapes here. Amorphous solids, on the other hand, from the Greek word without form, or rather, amorphous is actually a Greek word that means without form. Okay, and this type of solid lack the order in crystalline solids. So it says here, at the atomic level, the structures of amorphous solids are similar to the structures of your liquid. Amorphous solids do not have well-defined faces and shapes of a crystal. So, pag yung sa crystalline solid po, we have very definite patterns. For amorphous solid, they do not have any patterns. An example of this is your glass. Glass is a type of an amorphous solid. That's why, di ba yung glass, pag kunyari nahuhulog siya or nag-break siya, hindi mo makikitaan ng pattern yung mga pieces na nag-break, just like in this particular picture, di ba? They vary in sizes and in shapes whenever they break. Kasi nga, it's an amorphous solid. They do not have any form. Another example is your rubber. Parang yung rubber kasi very malambot siya. So, it really doesn't have any molecular or atomic form. Okay, that we will be discussing later on. So, among the two structures of solids, we will mainly focus on your crystalline solids. Or your crystalline solids are commonly denoted as your crystals. Okay? So, dun po tayo magfo-focus kasi yun po yung may shape and pattern. Sa amorphous solid, walang shape or pattern. So, it says here, because a crystalline solid, oftentimes called your crystals, consists of repeating patterns, we can draw these patterns in a three-dimensional figure called your crystal lattice. So, parang structurally, pwede nating i-drawing yung, pwede nating i-drawing yung structure ng isang crystalline solid. And that three-dimensional figure, which represents the solid, is called your crystal lattice. So, parang ganito yung itsura niya. Let's, parang imagine na itong mga to, yan yung either ion, or atom, or molecule. Tapos, syempre, diba, yung mga, yun is magkakadikit. So, parang idodrawing natin siya as this way para mas ma-imagine natin how they actually look like in a molecular level. So, as you can see here, we can represent the entire crystal by drawing the structure of the smallest identical unit that, when stacked together, form the crystal. So, for example, ito yung smallest unit that can represent the totality of the crystalline solid. Kumbaga, parang if we try to imagine, diba? For example, your sugar granules, parang yung isang granule is still a representation of the whole bag of sugar. Parang kunyari meron ka 1 kilo ng asukal. Diba? Yung pinakamaliit na butil is still sugar. So parang ganun po yung pwede natin gawing imagination when we talk about crystal. So you have what we call your unit cell. Tapos, pag yung unit cell mo, pinagpatong-patong mo, diba, you will have your crystal lattice, and that particular crystal lattice will represent the totality of the crystal. So, parang ganun po yung pwede natin gawing representation for us to understand your crystals in the smallest possible unit. Okay? Alright. So, now that we already have that, let's go now to what we call your unit cells. So, what is a unit cell? Nabanggit ko naman na siya kanina, but let's dig deeper on what it really means. So, it says here, a unit cell is a relatively small, mali ako dito. So, this is a grammatical error. So, a unit cell is a relatively small repeating unit that is made up of a unique arrangement of atoms and embodies the structure of the solid. So, the structure of the crystal can be built by stacking this unit over and over in all three dimensions. So, as you can see here in the figure, di ba yan yung ating unit cell, and then this is another unit cell. So, kumbaga pag in-stack mo yung unit cell together, di ba, pag pinagpatong-patong mo siya, pinagdikit-dikit mo siya, you could actually embody the whole structure of your crystalline solid. So, imagine niyo na lang na sa isang bag or 1 kilo, for example, ng asukal, yung pinakamaliit na granule is yung unit cell. Kasi it will still be sugar. It's just that it is in the smallest form. Parang ganun. So it says here, there are 7 fundamentally different kinds of unit cell which differ in the relative lengths of the edges and the angles between them. Each unit cell has 6 sides and each side is a parallelogram. Let us take a closer look at each of the 7 types. Kumbaga, pag in-imagine mo yung unit cell, syempre 3-dimensional yan, di ba? So, we will represent the 7 types of unit cell following the edges and the angles. So, if you take a look at the figure here, di ba, you have your y-axis represented by your letter C, your z-axis, ito ba yung z? Yeah, well, kunyari na lang. That's your z-axis represented by your A, and your x-axis represented by your B. So, kumbaga yung sides are represented by your edges A, B, and C. And then the angle that each side made with each other is represented by your Greek letters alpha, beta, and gamma. So parang ganyan siya. So you have your sides and then you have your angles alpha, beta, and then your gamma. So ganyan po natin i-imagine ang bawat unit cell. Kasi unit cells for different types of solids are different. Kasi hindi naman yan lahat cubic or hindi naman yan lahat is pare-pareho ng structure. So we will dig deep on how these unit cells actually look like. So let's have your first unit cell. We call this your cubic unit cell. It's the simplest among all of the unit cells. So parang madali lang naman siya kasi it's simply a cube. So ibig sabihin, pag cube yan, 'di ba? Your tawag dito, your line A, ito po yung line A, is equal to your line B and is equal to your line C. Kasi pare-pareho sila ng size ng edges or yung length po ng edges. And of course, since it's a cube, you all know that the angles alpha, beta, and your gamma are actually equal to 90 degrees. Kasi the sides are perpendicular to each other. So yan po yung isang type ng unit cell. Para lang siyang cube. So, cubic unit cell. Imagine niyo yung granule ng sugar is a perfect cube. Parang ganun po. And you have the second type of your unit cell, which we call your tetragonal unit cell. Now, when we say tetragonal unit cell, as you can see, di ba, si angles A, or rather si side A is equal siya sa length ni side B. So, you have a square there. So, side A is equal to side B. However, side A and side B is not equal to your side C. So, as you can see here in the figure, pwedeng mas mahaba si side C, pwede rin naman pong mas maikli si side C. So, hindi siya magkakapareho ng size. And although the angles that they make with each other are 90 degrees, which means na they are perpendicular to each other. Kumbaga si side C lang po yung naiba. Okay? So your side A is equal to your side B. However, they are not equal to your side C. Although all of the angles alpha, beta, and gamma is equal to 90 degrees. So yan po yung second type ng unit cell. Your tetragonal unit cell. And then we have the third one, your orthorhombic unit cell. Now, when we say orthorhombic unit cell, makikita nyo naman dito, these are the edges and these are the angles. Ibig sabihin si side A, hindi na siya equal kay side B, and hindi na din siya equal kay side C. So, no sides are equal. That's why you have that sign. Diba? Yung equal sign na may slash. Ibig sabihin, not equal. Although all of your angles are equal to each other, which is 90 degrees. So, hindi lang sila magkakapareho po ng length. Although the angles they make with each other is equal to 90 degrees. We call that your orthorhombic unit cell. The fourth one is called your monoclinic unit cell. So as you can see here, the sides are not equal. So your side A is not equal to your side B, and they are not both equal to your side C. So, and a special case here is that although your angles alpha and gamma is equal to 90 degrees, your beta is not equal to 90 degrees. Kaya if you get to see the figure, medyo nakatilt siyang pag ganon kasi hindi na po 90 degrees yung ating beta angle. So again, for your monoclinic, no sides are equal. Your alpha and gamma angle is equal to 90 degrees. However, your beta angle is not equal to 90 degrees. The fifth type of your unit cell is what we call your hexagonal unit cell. When we say hexagonal unit cell, as represented by this particular figure, your angle A, or rather your side A, is equal to your side B. So, para siyang square. However, yung side C mo is not equal to your A and B. So, parang in this particular figure, mas mahaba si side C. And when we talk about angles naman, your angles alpha and your angles beta, diba? Yung angle alpha mo and beta is equal to 90 degrees. However, your gamma, itong paganyan dito, your angle gamma is equal to 120 degrees. Hence the name hexagonal unit cell. Kasi si gamma is 120 and your alpha beta is 90. So that's the fifth one. Now, the sixth type of your unit cell is what we call your rhombohedral unit cell. So when we say rhombohedral unit cell, you can see here from the figure that your sides A is actually equal to your side B and it is equal to your side C. Diba? Para siyang cube. However, the main difference here is that although your angles alpha, beta, and gamma are equal to each other, hindi sila 90 degrees. So kung makikita nyo as a representation of the figure, it's a cube but it's tilted. Nakatilt siya kasi po yung mga angles, although they are equal, hindi sila 90 degrees. And lastly, we have your triclinic unit cell. So as represented by this figure in your in the right side of your screen, you have your side A is not equal to your side B, is also not equal to your side C, and all of the angles are not equal to 90 degrees. So yun lang naman po yung triclinic, wala pong equal na edges or angles. Okay? So of course, among all the 7 unit cells that we have been discussing so far, we will focus primarily on your cubic unit cell, in which all sides have the same length and all angles are 90 degrees. Pero yung concept po na introduce natin next, they apply to all the types of unit cells. Kasi aside from being a cubic unit cell, meron pa po yung subtypes. Okay, so all of the unit cells discussed, you have 7, may subtypes pa po yan. Although yung unit cell na we will be talking about the cubic unit cell particularly, kasi siya yung pinakamadaling intindihin, and the concepts that will be introduced, nag-a-apply din siya sa the rest of the unit cells discussed. So you have there, so let's introduce now your cubic unit cells. So imagine that this is your cubic unit cell and we place certain points in each of the 3 unit cell to introduce the 3 subtypes of the unit cell. So you have here the first one. Imagine maglalagay tayo ng parang, for simplicity, let's imagine that we will place an atom strategically on the edges of that particular unit cell. So it's represented by this particular figure. So this is what you call your simple cubic unit cell. Kasi yung atoms niya nandun lang sa, kumbaga, edges ng inyong cube. And we also have the second type of your cubic unit cell. So aside from the 8 atoms strategically placed in the corners of the cube, meron kang isa pang atom doon sa gitna. And the third type is what we call your face-centered cubic unit cell. So it's simply parang meron kang 8 atoms strategically placed at the corners of the cube plus an additional atom in each face of the cubic unit cell. Kumbaga sa bawat side niya, meron pang isang atom. Meron dyan, meron doon sa likod, of course sa baba and sa taas. So that's one. We will take a closer look at each one of them. So your cubic unit cell, this one is simply called your simple or primitive cubic unit cell. So, di ba yung figure kanina, as I said, it is strategically placed at each corner of the cube. Di ba? Ganyan siya. Pero, in reality, di ba? In reality po, di ba hindi naman po nag-exist yung distances na yan? Kasi if we represent this particular sphere as an atom, your atoms are closely packed together. So, in reality, wala naman talaga yung mga rods na yan. It actually looks like this. Diba? Parang magkakapatong sila eh. So, it actually looks like this. And your cubic or your simple primitive cubic cell is this one. Parang siyang dito siya, kinat po siya dito sa loob. Yan. So, pag kinat natin yan, kunyari yung center, from center to center, ikakat natin yan. So, ganito po yung itsura ng ating cubic unit cell. So, in reality, this is what a unit cell looks like. Okay? Pag we try them to imagine. The next one is what we call your body-centered cubic unit cell. So, di ba kanina in the previous slides that we have, you have 8 corner atoms, and then you have 1 atom strategically placed in the center of the cube. So, in reality, yung mga atoms, ganito po yung kanyang pagkakapack. Diba ganyan? So, merong isa doon sa gitna, and then of course, your 8 corner atoms. And if we try to get that particular cubic unit cell, ganito po yung itsura niya. So, of course, you have 1 in the center, and you have the 8 corner atoms. And lastly, your face-centered cubic unit cell. So, as I've stated earlier, aside from the 8 corner atoms, meron ka in each face of the cube. So, meron sa taas, sa baba, sa right, sa left, and of course, sa front and back. Such that, if we take a closer look at how it actually looks like, diba? Wala naman po talaga yung mga rods na yan. Ganito yung itsura niya. Para siyang na-compress. Ganyan. And if we try to get the cubic unit cell or the unit cell in this particular shape, ganito po yung kanyang magiging itsura. That's how a face-centered cubic unit cell looks like. Diba? So as I said, cubic unit cell yung pinag-uusapan natin. Pero all of this simple, body-centered and face-centered unit cell is applicable to all types of unit cell. Mas madali lang po kasi siyang ma-imagine when we talk about a cube kasi it's the simplest shape that we have among all of the unit cells that are presented. So it says here, please watch the video provided in the modules tab to understand the structures of the subtypes of unit cells, particularly the cubic unit cell. I will be posting a video in your modules tab in Canvas para po mas ma-imagine nyo siya how it actually looks like. Kasi medyo doon gumagalaw-galaw yung image. So, it's better na makita nyo siya visually, yung paggalaw-galaw para you get to understand these subtypes better. Okay, now let's go to the last part. We call this the packing of spheres. So it says here, our discussion of the three-dimensional structures of solid has considered only substances in which all of the components are identical. As we shall see, such substances can be viewed as consisting of identical spheres packed together in space. The way the components are packed together produces the different unit cells. Most of the substances with structures of these types are metals. So, ang sinasabi lang po natin, di ba, syempre, if you have an atom, di ba, pag nakita nyo naman po dun sa mga unit cells, di ba, they are closely packed together. Parang they are stacked, parang kumbaga mayroon siyang atom sa left, sa right, so, di ba, na-compress siya. Pero paano po ba nagpapatong-patong yung mga atoms na yon? That is what we will be talking about in this particular topic, your packing of spheres. So it says here, simple cubic structure. The arrangement of the atoms in the solid that has a simple cubic unit cell. Each atom in the lattice has only 6 nearest neighbors in an octahedral arrangement. Consequently, the simple cubic lattice is an inefficient way to pack atoms together in space since only 52% of the total space is filled by the atoms. The only element that crystallizes in a simple cubic cell is your element polonium. So very rare po yung magkakaroon tayo ng simple cubic unit cell kasi it's not very efficient in terms of packing. It's only your element polonium. Diba? So parang ganito, example mo yung isang sphere dyan is an atom. Diba? Para lang siyang nag-stack up on top of each other. So ito, pareho lang ng pagkakapack dito or pagkakastack and ganyan, ganyan. So pareho lang po kung paano sila nagpatong. Such that if you take a look, diba, ayan o, yan po yung inyong cubic unit cell. If we take a look at that. And pag punta ka dun sa may bandang gitna, so imagine mo, this is the atom na nasa gitna. Di ba parang ilang atoms ba yung naka-attach sa kanya? Of course, you have the atom on the back, on the front, and then you have the atom number 5 sa right side niya, the atom number 2 on the right, or rather left side of this atom is atom number 2, sa right side is 5, sa taas is 1, sa baba is 6. So kumbaga, sa isang particular atom, may 6 po na atoms na naka-attach. Yan po yung simple cubic structure. Now, let's take a look at the other type. So you have your body-centered cubic structure. So the body-centered cubic unit cell is a more efficient way to pack spheres together and is much more commonly among pure elements. Each atom has 8 nearest neighbors in the unit cell and 68% of the volume is occupied by the atom. So kumbaga, diba ito, nakita na natin ganyan yung itsura niya. But when a BCC is stuck together, ganito yung itsura niya. Imagine nyo yun yung center atom, diba? Tapos may naka-attach na, course, 1, 2, 3, 4, 5, 6, 7, 8. 8. Nandun sa likod. Yan. Diba parang ganito siya? 1, 2, 3, 4, 5, 6, 7, 8. So, sa isang atom na nasa gitna, merong 8 atoms na naka-attach sa kanya. And the volume sa loob is around 68%. So, mas efficient siya in terms of sa pagkakapack ng mga atoms. And it says here, as shown in the figure, the body-centered cubic structure consists of a single layer of spheres in contact with each other and aligned so that their centers are at the corners of the square. A second layer of spheres occupies the square-shaped holes above the spheres in the first layer. Ang sinasabi lang po dito yung diniscuss ko na kanina. Diba? Pag, kunyari meron kang 4 sa baba, parang yung susunod na layer is ilalagay doon sa parang gitna ng square na yun. Kung we imagine that these spheres are your atoms. So, ganun lang siya nagpatong-patong. That's how you do the BCC structure. The third layer of the spheres occupies the square formed by the second layer so that each lies directly above the sphere in the first layer. So, kung ano po yung, kumbaga, if this is your first layer, tapos yun yung second layer mo, yung third layer mo, parang the same lang siya ng pagkakastack dun sa first layer mo. Diba? So, yung, kumbaga dito sa structure na to, your first layer is packed the same as your third layer, and the same as your fifth layer, and the same as your seventh layer, and the same as your ninth layer. Tapos yung second, fourth, sixth, and eighth layer, pareho sila ng pagkaka-pack. It says here, all the alkali metals, such as your barium, radium, and several of the transition metals have a BCC structure. So, yan lang po yung example ng mga solids which follows this particular type of packing. And the third type of your spheres packing is called your closed pack structures. Among the three, this is the most efficient way to pack spheres kasi mas malaki yung volume na na-occupy ng atoms. So, you have two variants for this type of packing. You have your hexagonal closed pack, or we commonly denote it as your HCP. So, makikita mo dito, ganyan siya. And your cubic closed pack, or what we commonly know as your CCP, ganito naman siya. So, kumbaga si letter A, or si first layer, is pareho kay third layer. However, diba, dun sa BCC, yung second layer mo kasi, nakalagay siya dun sa gitna ng square. Ito, nakalagay siya dun sa depression. What we call your depression, or space in between the two atoms on the first layer. Tapos naman, ito naman, iba po yung third layer kung paano kasi naipatong si third layer. For you to understand it better, how these particular spheres are packed, Another video is provided to you in the modules tab. Mas maganda to kasi mas tag dito. At least ngayon, you have already an idea, and the video will just supplement the idea that you already have. So if we have a summary table, diba, percentage of space occupied by atom, you have this. For simple cubic, 52% of the volume is occupied. For a BCC, or your body-centered, it's 68%. Your hexagonal, your HCP, and your CCP occupy 74% of the total volume. So, mas preferred to kasi ito na po yung mga mas matitibay na solids. And when we talk about your coordination number as indicated here, kumbaga ito yung number of atoms na nakadikit sa kanya. 'Di ba parang sa simple cubic kanina, kung may atom ka sa gitna, yung neighboring atoms niya, ilan po ba yung neighboring atoms niya na nakadikit sa kanya? That's actually your coordination number. So for your simple cubic, it's 6. For your BCC, it's 8. For your HCP and your CCP, it's actually 12. So thank you for listening, class. We will be having the next topic, which is all about metals. And please do watch the video for you to understand it better. I'll be posting the video on metals probably on the same day or depende po sa situation natin. So that's it for this particular video. Thank you so much for listening. And stay home, stay healthy, and stay safe. Goodbye, everyone.